Here's a black hole. We imagine it as an enormous, super dark region in space that pulls everything toward it. And once something falls inside, it's dragged to the central endpoint called the singularity, where everything gets squished. Right? But what if we told you that's not exactly how black holes work? So, what's a singularity anyway? And what's really on the other side of this pitch black curtain? Get ready to discover a mind-bending work of black holes, where reality is way stranger than any fiction. Black holes are intricate space phenomena. Everything about them is complicated. When a large star, about 10 to 20 times more massive than the Sun, exhausts all of its fuel, the balance between gravity and pressure breaks down, and the star collapses in on itself and goes supernova. The problem with our current understanding is that we use different theories to explain phenomena happening on different scales. There's quantum field theory, which works well to explain intricate behavior of particles, ranging from atoms and down to the tiniest subatomic building blocks of matter. Apply this theory to astronomical scales, and it's of no use. For that task, scientists resort to Einstein's general relativity. Pick the right theory, and calculations generate correct answers. But black holes are tricky. At first, they're astronomical objects, large stars. And then they quickly shrink to much smaller, sometimes quantum sizes. For example, in order for the Sun to become a black hole, it would have to be squeezed to the size of just about 1.8 miles in radius. Theoretically, you can turn any object into a black hole. There's a formula that tells us how much something has to be squeezed to become one. This threshold is known as the Schwarzschild radius, and if you wonder just how our planet would have to be to turn into a black hole, imagine the entire Earth as a ball with a radius of 0.35 inches. But what if an object's radius is 0? Traditional calculations, both math and physics, become meaningless, and so we call this phenomenon a singularity. But does such a concept truly appear in the physical world? Let's try to break it down. Consider this thought experiment. If you wanted to make the simplest version of a black hole, you'd start with tiny bits of matter floating around in space. They don't push against anything, but just hang there. So they're like small specks of dust floating very close to each other without moving around much. But in space, there's gravity, and so it starts pulling it all together, reducing space in between dust particles. Over time, little specks of dust start to squeeze tighter and tighter, eventually reaching a point where their combined mass and gravity grows so intense, space around them starts to compress, and this creates an event horizon, a kind of boundary that lets things in but doesn't really allow anything to get out. This type of black hole is called a Schwarzschild black hole. It has mass, which is just how much stuff went into making it, but it doesn't have any electric charge or spinning motion. Now think about what happens when you cross the event horizon of such a black hole. For the sake of experiment, let's say it's large enough for you to enter with a spaceship. Once in, you panic and try to get out by firing thrusters to accelerate back out. Physics says that regardless of the direction the ship is facing, you'll still be drawn toward the central singularity. To understand this, imagine a long, narrow corridor with no way out except through a door at the end. Once you step into this corridor, the door shuts behind you, and there's no way to open it again. The corridor has a moving walkway, much like the travelator in an airport, and it's taking you forward at the speed of light. No matter which way you try to move, either running in